Hey everyone, just letting you know that for the plan is I'm gonna go into like Kirchhoff's laws and stuff after this, but first I want to show you resistance in general. I don't know how many tutorials it's gonna take on resistance, but I want to go thoroughly through it, explain what a resistor is, um, different elements of it, what it depends on, and then we're gonna go into equivalent resistances, explain a little bit about that, and then that's going to conclude the resistance tutorial, unless I can think of anything further. But we'll start here with the symbol of a resistor, which is this like shark toothed symbol here that I'm going to box in red. Alright, now these are just you can think of them as wires in the circuit, but basically wherever that line that I drew touches is where a wire would in a circuit. It just means that they're connected. And a resistor, the voltage drop across it from let's say here, if you were to place a voltmeter on these two red beads, the voltage drop across it, I'm going to call it V, will equal 0 if the current across it is equal to 0. I mean, note the current with a green arrow. If you have current going through this thing, we can figure out what V is, because we know that V is equal to I times R. So you would plug your current in, and you would plug your resistance in, and you would find the voltage from this red tick to that red tick. A lot of arrows there. A resistor depends on material and geometry. If you had to give resistance a technical name, I would say that it is a passive passive two-terminal circuit element. And that's what a resistor is. But I don't really want to talk about a resistor. I want to talk about resistance, and they are different. Sorry, my phone keeps going off. And resistance is different from a resistor in that any passive element in your circuit can have a resistance. It doesn't have to be a resistor. A light bulb can have a resistance. I don't know, whatever, a computer screen, you name it. If it's got current going through it and it's got a voltage drop across it, it has to have some sort of resistance due to Ohm's law. So I'm going to scroll down here, and well, before I scroll down, I might as well just pull the damn thing down. And excuse my language. And we're going to start with resistance and what it. Let's jump to here, just because I want to show you more of a definition type approach. So I'm just going to read this for you, in case you can't see it. I guess I could blow it up. Maybe I can't. Oh, look at that, I can. The electrical resistance of an electrical element measures its opposition to the passage of an electric current. The inverse quantity is electrical conductance, measuring how easily electricity flows along a certain path. Electrical resistance shares some conceptual parallels with the mechanical notion of friction. The SI unit of electrical resistance is the ohm, while electrical conductance is measured in Siemens. An object of uniform cross-section has a resistance proportional to its resistivity, and length and inversely proportional to its cross-sectional area. All materials show some resistance except for superconductors, which have a resistance of 0. The resistance of an object is defined by the ratio of voltage across it to current through it. What a bunch of mumbo jumbo. Alright, so that's what resistance is. I'm sure you already guessed it resists things. It's kind of trivial. I showed you this because I didn't really want to write it all down. Electrical conductance is the inverse, so 1 over your resistance is your electrical conductance of something. I'm sure there's a notation here. There's a certain relationship between friction and resistance. I wonder what the relationship between conductance and some mechanical notion would be. But anyhow, I'll go back to the thing. Let's go down to our notes here. Now you know what resistance is. It just resists your current, which is weird to think about because if you have all this current coming in, and then it hits this resistor, and it starts building up, seems like this current would start piling up, and this current would be coming out at a slower rate. I don't know. It doesn't even matter. I just need to erase. Alright, so equivalent resistance. Pretty simple. Resistance is, I'm going to denote these as a resistor. They are a circuit element, so they do have a resistance. And if this is X, and this is Y, and this is Z, and this is H, for some ungodly reason, the equivalent resistance, Req, of this circuit would be X plus Y plus Z plus H. Okay? That's really straightforward. You always add things in series. Your problem comes when you start dealing with a parallel resistance. Parallel resistance is a bit harder, just because you have more to do and more to think about. But parallel resistance, like I said, is we had these for resistors, and then I had some voltage across them, and this was X, this was Y, and this is Z. The equivalent resistance across these two red points here will be basically you add up their conductances. If you were trying to find the conductance for this, you would add these together. And what it is it's, at least I think so, I could be just talking on my butt. It's 1 over X plus 1 over Y plus 1 over Z. And that will equal your, what the heck, Req. I'm going to smash my computer in a minute. And I guess a better way to write this whole thing, even how I enter it into the calculator, is a lot easier. Say X to the negative 1 plus Y to the negative 1 plus Z to the negative 1. And all this has to be over 1, so that's the negative 1. And in case you're confused about the whole negative 1 thing, it's just a mathematical way of writing, like, 1 over something. 1 over X is equal to X to the negative 1, because anything to the negative power will shift it down into the denominator. So basically I just wrote all that with notation of negative 1. It's easier to put into your calculator and makes things a lot quicker to find. There are shortcuts. If, for instance, you only had X and Y, forget about Z. If you only had X and Y, a shortcut for this, a shortcut for this would be X times Y over X plus Y. And that would also equal your Req. You can only do that when you have 2. Another shortcut would be if you have 2 of the same things, if it's X and X, if both of these here are X, then you can just take X and divide it by 2, and you will get your Req. And I can prove that real quick. You can have x times x over x plus x. And what you actually get here, and what this actually equals, is x squared, because x times x is x squared, over 2x, and ultimately this x will cancel, the square will cancel, and you'll get x over 2. So there's a little derivation, I guess, to prove that formula. But there you have it. It's I'll do an example if I have time. I have no idea how long this was running. Alright, just figured it out with my program. About 10 minutes in now. I'll just do a really quick video. The next video I'll do will be an example on resistance. So, finding equivalent resistance. So, an example on finding REQ will be in my next video. So, tune into that one and see what the fun's all about.